Thank you for joining me in the History of Science collections of the University of Oklahoma Libraries. Let's see what stories await us from the vault that will throw light on medieval Islamic science. This is the oldest Islamic manuscript in the History of Science collections. We think it may date to about 1100. Does it look like it was dug up somewhere? The manuscript is written by hand on paper. It is beautiful. The only problem is that we don't know what it is. Several scholars have examined it, yet it remains something of a mystery. It is some sort of collection of Persian stories about animals, perhaps like Aesop's fables. So we are looking for scholars to help us solve this mystery. Here is another manuscript that is something of a mystery. It too is written on paper. The secret of making paper was obtained from Chinese prisoners of war in the 8th century. Since paper was much cheaper than papyrus or parchment, manuscripts could be made available at relatively affordable costs. For example, you might sell a donkey instead of about 30 sheep. By the 11th century, a technical work like Ptolemy's Almagest could be expected to lie within the reach of determined scholars. This manuscript is clearly an introduction to astronomy, but we're not sure who wrote it. Many years ago, a scholar described it as the work of Al-Ghazali, who flourished around 1000. This scholar dated it to the 1400s or 15th century and called it the earliest of 3 known manuscripts by Al-Ghazali. However, we now suspect that it is not by Al-Ghazali, so it needs more attention. A student is now working to digitize both of these manuscripts. With the assistance of the OU Library's Digitization Laboratory, perhaps together we will solve these mysteries soon. Jabir ibn Hayyan, later known as Geber in Latin, was an alchemist at the court of Caliph Harun al-Rashid, who flourished around 800. This edition of Geber was printed in 1529. Many of the works which circulated under his name originated in the 10th century near Baghdad. Others, like the Summa Perfectionis, probably originated in Latin Europe. Jabir's alchemy was both a spiritual discipline and an empirical science. He developed new laboratory apparatus, improved standard techniques such as distillation and crystallization, and pioneered chemical preparations of various kinds, including acetic acid, tartaric acid, sulfur, and mercury. Medieval alchemy was a demanding spiritual, experimental, and theoretical tradition which provided ideas, techniques, and motivation for the widespread pursuit and development of chemistry. For example, both Isaac Newton and Robert Boyle were familiar with Geber. Dozens of Jabir's works became intermixed with writings by a Latin pseudo-Geber who flourished around 1250. This edition was published in 1541. It contains several works by both Jabir and pseudo-Geber as listed on the title page. These works were avidly studied by later chemists. The collection's copy of this rare edition is heavily annotated. This early reader may have lived around 1644. These annotations have not yet been studied. But on this page, one can read about both bismuth and quicksilver. This copy, like our manuscripts, awaits its first researcher. Muhammad al-Baghdadi, who flourished around 1000, wrote several treatises in mathematics. This one, printed in 1570, explains a method for dividing surfaces. This edition was printed by the famous Renaissance mathematician Federico Commendino. The manuscript for this text was brought to Commendino by the Elizabethan mathematician John Dee. This is the great treatise on medicine by Ibn Sina, known in Latin as Avicenna, who flourished around 1000. Ibn Sina's Canon of Medicine became a standard medical text in European universities. Near the bottom of the frontispiece, in the center, the vignette ranks Ibn Sina among the four greatest physicians: Galen, Hippocrates, Ibn Sina, and Aetius. Ibn Sina's canon was printed in Venice in 1608. 20 years earlier, in 1588, the same printer issued the first collected edition of the Hippocratic Corpus. The frontispiece is the same, an early modern version of clip art, except for the area for information about the title and contents. But the central vignette at the bottom that ranks Ibn Sina, along with Hippocrates, among the four greatest physicians remains. This work on geography is by Drusa, who flourished around 1150 in Sicily. Drusa, a renowned geographer, recounted voyages to Iceland and to the Sargasso Sea. This work is in Arabic, but it's not a manuscript. It was printed with movable type in 1592. Printing Arabic with movable type is something of a technological feat, but this book was not printed in Baghdad or Cairo. Because of the widespread European interest in works of Islamic science, even as late as the generation of Kepler and Galileo, the Medici set up a press to print Arabic works in Rome. This work by Drusa is therefore one of the first books printed in Europe in Arabic. And here we have Abu Mashar's Introduction to Astrology. As a practical manual, it proved very influential. Many editions were read by Albert the Great, Roger Bacon, Pierre Dailly, and Pico. The History of Science Collections holds 3 copies of Abu Mashar, printed in 1489, all different. Abu Mashar was one of the most prolific writers on astrology during the Middle Ages, and this work was the most frequently quoted astrological text in the West. This first edition was printed by Erhard Ratdolt, an important early printer of books in science and mathematics. This copy is bound in a much older, discarded sheet of vellum, recycled in 1489 to make the binding of this book. And here I have it open to the page describing the constellations of the zodiac. The astronomer Al-Farghani flourished around 850 and worked in Baghdad and Cairo. His introduction to astronomy, shown here, was studied by Dante. Al-Farghani also calculated the diameter of the Earth and wrote a treatise on the astrolabe. In this work, Al-Farghani explained how solid spheres might carry the planets around eccentric circles in a physical manner that was consistent with Ptolemaic astronomy. This medieval introduction to astronomy is a sequel to a treatise on the formation of the heavens and the earth. It's not in Arabic, is it? This was written by a Jewish mathematician and astronomer in Barcelona, also known as Savasorda, who is credited with the earliest solution of the quadratic equation. In this beautiful edition, Abraham Barhia wrote in Hebrew. His Hebrew text appears beside a Latin translation. This work shows us that by Islamic science, we are referring to science in a cosmopolitan culture that was shaped by the Islamic faith. Arabic language was predominant, but most people were not of Arab ethnicity. And the authors of these scientific texts might have been of any kind of Middle Eastern extraction: Persian, African, Jewish, or European. The historian of Islamic science, A.I. Sabra, explains, "It was through the vehicle of Arabic that a non-Arab scholar in 11th century Nishapur or 15th century Samarkand had access to the results arrived at in 9th or 10th century Baghdad, and an astronomer working in 14th century Damascus became acquainted with writings produced in 11th century Cairo, 12th century Spain, or 13th century Mariga. With the decline of Abbasid power and the eventual breakup of the Abbasid Empire, centers of learning multiplied across the Islamic world, following the proliferation of dynastic rules that vied with one another for cultural and intellectual eminence, as well as for political power. Unfortunately, two stereotypes have profoundly shaped modern perspectives of Islamic science. First is the alleged lack of originality. Pierre Duhem, an early 20th century French physicist, was also a pioneer historian of science who's written these volumes on medieval science. Yet a century ago, Duhem wrote, "There is no Arabic science. The wise men of Mohammedanism were always the more or less faithful disciples of the Greeks, but were themselves destitute of all originality." The second stereotype is that Islamic science flowered briefly during the Middle Ages, but was not long sustained. In this view, the chief question about Islamic science is the problem of its decline. But to frame the discussion around the so-called problem of its decline presupposes that it did in fact rapidly decline before the end of the Middle Ages, rather than being much longer lived. Yet scholars now believe that vigorous, original scientific activity in the Islamic world extended up through the early modern period and even into the 18th century, although we do not yet know enough to describe it. These later Islamic manuscripts remain largely unstudied and unexamined. In geology, for example, I have seen clear examples of European writers in dialogue on the history of the earth with their Islamic Mediterranean neighbors in the 17th and 18th centuries. So these two stereotypes, the lack of scientific originality and the assumption of a brief duration and rapid decline, profoundly shape modern perspectives of Islamic science. Let's answer these two misconceptions by turning to the first printed edition of Ptolemy's Almagest, published in 1496 by Regiomontanus. Regiomontanus was the first European astronomer to fully master Islamic astronomy. Far from merely translating Ptolemy's Almagest, Regiomontanus's edition was a major contribution to Renaissance astronomy. It contained new techniques, methods, observations, and critical reflections. This was state-of-the-art astronomy when Copernicus was a young man, and Copernicus studied it carefully. Noel Sverdlow has argued that the diagram on this page of Regiomontanus provided the major step in the transformation to a sun-centered model. Here, Regiomontanus proved that eccentric models could be used for all of the planets instead of epicycle models, except for retrograde motion. This proof was denied by Ptolemy himself, but it was included by Regiomontanus in this edition of the Almagest. Copernicus then took the next step by putting the sun in the center. In this photograph, Jamil Rajab is holding the Oklahoma copy of Regiomontanus open to the same diagram. Rajab has recently shown that the 15th century Islamic astronomer Ali Kushji, a generation before Regiomontanus, used an identical diagram to make the same proof. If we say that Regiomontanus paved the way for Copernicus, then we can say the same for Ali Kushji. In other words, if we were to ask Noel Sverdlow or Jamil Rajab to explain the mathematics, they would show how Ali Kushji and Regiomontanus were making it easy for the next person to get the idea of transposing the positions of the Earth and Sun. Copernicus picked up where Ali Kushji and Regiomontanus left off. Indeed, in the manuscript, Ali Kushji himself went on to comment that a moving Earth is impossible to disprove. Contrary to Pierre Duhem, I would call that original. Let's go back and take another look at Regiomontanus. On this page, Regiomontanus exclaimed, "Sed miram est," what a marvel. At the end of Book 5, Section 22, Regiomontanus is here calling attention to the astonishing fact that Ptolemy's lunar model required the moon occasionally to appear 4 times its usual size. This impossible wonder arrested the attention of Copernicus. To correct for this anomaly, Copernicus used a crank mechanism. It is one of Copernicus's most significant technical advances over Regiomontanus, who could only emphasize the problem. But how did Copernicus come up with a crank mechanism that could solve this problem pointed out here by Regiomontanus? The answer is from Nasr al-Din al-Tusi. Al-Tusi flourished around 1250. He worked in Baghdad and in the observatory of Mariga in modern-day northwest Iran. This is Al-Tusi's edition of Euclid's Elements of Geometry, published by the Medici Press in Rome in 1594. Again, it is printed in movable type, just like Idrisi. The existence of this printed edition is proof of the great interest by European scientists in the Renaissance in the texts of Al-Tusi and other Islamic scientists. So this is Al-Tusi's explanation of Euclid. But on this page, Al-Tusi works out the geometry of one circle moving within a larger circle to produce a so-called crank mechanism. Al-Tusi employed a crank mechanism like this to solve the problem of the motion of the moon pointed out 300 years later by Regiomontanus. In the De Revolutionibus of Copernicus, published in 1543, Copernicus also used Al-Tusi's crank mechanism for his model of the moon's motions. Regiomontanus had not heard of it in 1496. Somehow, by 1543, Copernicus had. I'd call the crank mechanism of Al-Tusi, employed by Copernicus, original. The historian of Islamic science, George Salaba, comments, "One still has to find a name for the production of the Tusi couple that was first encountered in an Arabic text written by a man who spoke Persian at home and who used that theorem, like many other astronomers who followed him, and were all working in the Arabic Islamic world, in order to reform classical Greek astronomy, and then have his theorem in turn be translated into Byzantine Greek toward the beginning of the 14th century, only to be used later by Copernicus and others in Latin texts of Renaissance Europe. What name could one possibly dream up for that kind of science? And whose science was it anyway?" Ibn al-Haytham, known in the Latin West as Alhazen, made significant contributions to both astronomy and optics. In astronomy, Ibn al-Haytham founded a tradition of Islamic astronomical investigation that sought to bring together Ptolemaic geometrical models with plausible physical mechanisms. This tradition led through Al-Tusi to Copernicus. In optics, Ibn al-Haytham founded a tradition of mathematical optics that provided a basis for the later investigations of Kepler and Galileo. This copy is the famous Risner edition of Alhazen's optics. The frontispiece displays a variety of optical phenomena, from reflection and refraction to the bridge that shows perspective and the optics of the rainbow, to the scene of burning mirrors used to defend the city of Sicily by Archimedes. This experimental treatise in optics built upon the foundation laid by Ptolemy and provided a basis for later investigations by Wiedelo, Kepler, and others until the invention of the telescope in the early 17th century. Historians used to speak of a scientific revolution in a way which supposed that the story of science belonged to the heritage of early modern Europe. But consider the Selenographia by Johann Hevelius, published in the middle of the scientific revolution, less than 40 years after Galileo's first telescopic discovery of mountains on the moon. This book fulfilled Galileo's lunar land run, the race to map its surface. This is the first true lunar atlas. Dozens of fine engravings detail the surface of the moon as it appeared each clear night over a period of 5 years. From the varying shadows cast by topographical features along the changing shadow line, Hevelius constructed a composite map of the moon. It's accurate enough to plot the Apollo lunar landings. Yet on the frontispiece, Hevelius himself celebrates not the triumph of the European scientific tradition, but the heritage of Islamic science. On the left is Ibn al-Haytham, the leading medieval Islamic astronomer and optical theorist. On the right, holding the telescope, is Galileo. Who would have guessed that one of the most impressive works of the scientific revolution portrays Galileo in Islamic dress as a tribute to the tradition of medieval Islamic science? This frontispiece of Hevelius reminds us that the growth of Western science cannot be understood apart from rich and sustained interactions between multiple cultures. It is impossible to separate the European scientific revolution from the achievements of medieval Islamic culture and other civilizations which came before. Science is a story. What stories do you want to hear and tell about Islamic science?